Hello everyone, welcome back to my YouTube channel. In this week video, I'm going to explain to you how you should answer test 1 questions. Altogether, we have 6 questions and let's start with the first one. Question number 1. 2.24 atm of xenon gas and 4.27 atm of fluorine gas were allowed to react, resulting in the formation of xenon tetrafluoride. At equilibrium, the pressure of xenon gas was found to be 0.34 atm. Determine the equilibrium constant Kp for the reaction. Alright, in order for us to answer this question, the first thing we need to do is to write a balance equation for the reaction. This reaction is between xenon gas and also fluorine gas. Given in the question, it states that it will form xenon tetrafluoride. Therefore, when we want to balance out this equation, because we have 4 around here, we only have 2, so we need to times 2. So this is the balance equation for this reaction. The next thing we need to do is to write the ice diagram. So the ice diagram, so we will have xenon plus 2 fluorine gas. It will produce xenon tetrafluoride. Alright, so initially, the ATM, the initial pressure, so for xenon is 2.24 atm and for fluorine gas is 4.27 atm. So basically we assume that there is no xenon tetrafluoride that is produced at the beginning of the reaction. So here we need to minus x minus 2x plus x. Therefore we will get 2.24 minus x, 4.27 minus 2x, and here is x. In the question, it is stated that the pressure of xenon gas was found to be 0.34 atm at equilibrium. So at equilibrium, the xenon gas, the pressure is equivalent to 0.34 atm. Therefore, 2.24 minus x is equivalent to 0.34. So where do we get this value? Is from here. Right. Therefore, you will get your x is equivalent to 0.34 minus 2.24. Hence, your x is equivalent to 1.9. So what we need to do now is we need to substitute all this value of x with 1.9. In saying that, because we already know that this value is 0.34 and for xenon tetrafluoride is the value of x itself. So what we need to calculate now is the value of fluorine gas. So we are just going to substitute the x with 1.9. Alright, so what we can do is now we are going to calculate the partial pressure for fluorine gas. So the partial pressure for fluorine gas at equilibrium is equivalent to 4.27 minus 2x, whereby your x is equivalent to 1.9. So you will get the partial pressure for your fluorine gas is equivalent to 0.47. So when we plot again at equilibrium, it should be 0.34, 0.47, and this one is 1.9. So this one is for xenon, this one is for fluorine gas, and this one is for xenon tetrafluoride. Alright, so from the calculation that we have done just now, we know that the partial pressure at equilibrium for each component. So therefore, we can calculate the Kp. So the Kp is actually equivalent to whatever in the product, which is the xenon tetrafluoride, divided by whatever in the reactant, so partial pressure of xenon times the partial pressure of fluorine gas, but because we have 2 around here, so to the power of 2. So we need to plug in the value 1.9 over 0.34 times 0.47 square, right? So you will get your Kp should be equivalent to 25.2975. Right, so bear in mind, in the question, you were asked to determine the equilibrium constant Kp for the reaction. So this is the final answer for the first question. Question number 2. A chemist hypothesized that 89.2203 gram of water shall be produced by the combustion of 58.20 liter of methane at STP, assuming there is excess oxygen throughout the reaction. Explain if the hypothesis made is accurate. Alright, so the same as the first question just now, the first thing that you need to do is you need to be able to write a balance equation for this reaction. So this reaction is actually between the methane and it is a combustion reaction. Therefore, we write methane, and then in a combustion reaction you need oxygen. So you will have to produce water and also carbon dioxide. So this is a very simple equation for a combustion reaction. So now what you need to do is you need to balance out the equation. So here you have 2 oxygen, here you have 2 oxygen, but you have another oxygen around here, and you need to have 4 hydrogen, and you already have 2 hydrogen around here. So what you can do is you need 2 times 2. Therefore, your hydrogen 2 times 2 equivalent to 4. This one is settled. And you have 1 oxygen over here. So you're okay with that. So you have a summation of 2 plus 2, which is 4 oxygen. So you need 2 times 2 over here. So this is your balance equation. Alright, so the next thing that we need to do is we need to use the ideal gas law. So the formula is PV equivalent to nRT. What we are going to look at is the pressure. So the pressure is at STP. So STP, your pressure is 180 m and your temperature is 273 Kelvin. So your pressure is 1. So the volume is 58.2 liter is equivalent to N. So your R is the gas constant 0.0821 and your temperature is 273 because just now we already state that it is at STP. Therefore your N, the number of mole, is equivalent to 58.2 divided by 0.0821 times 273. Therefore, you will get the number of mole for your methane is equivalent to 2.5967 mole. Right, so the next thing that we need to do is we need to write the ratio between the methane and also the formation of water, because it hypothesized that this much of water shall be produced. So from the equation, we know that 1 mole of methane will produce 2 mole of water, right? So from our calculation,
we have this much of methane. So 2.5967 mole of methane should produce 2 times 2.5967. So this is equivalent to 5.1934 mole of water. Right. But given to you in the question is the mass of water. So from this number of mole that you have calculated, you need to convert it into mass. Alright, so since we need to calculate the mass, so we are just going to use the formula of number of mole is equivalent to mass over RMM. So the number of mole that we are looking at is the number of mole of water, so H2O. So the number of mole is 5.1934, and then you need 2 times the RMM for water. So water H2, so you have 2 mole of H, so 1.0079 plus your O is equivalent to 15.9994. So you will get your mass is equivalent to 93.5601. So what you need to do now is to compare this value with the value that they provide in the question. It is not the same, therefore the hypothesis is not accurate. Right, so this is the final answer for the second question. Right, let's move on to the third question. Determine the molar enthalpy of formation for the reaction between ethane and oxygen from the following equation. So basically this is a Hess law. So what you need to do is you need to use all of this equation and then until you get your target equation. So basically your target equation is just 1 mole of the reaction between ethane and oxygen. Alright, so the easiest way to answer this question is for all the equation, what you can do is you need to times 2. So all of this we need to times 2. So the next step is you need to flip over the equation number 2, whereby the reactant should be at the product and the product should be shifted to the reactant. So at the end, you will get the equation as such. The identical elements that we can slash out. For example, here we have 2H2 at the reactant and we do have 2H2 at the product. Same goes with C2H4. We have one at the reactant and another one at the product. Okay, so after that we will get whatever is left is 2C2H6 plus 7 oxygen will produce 4 carbon dioxide plus 6 mole of water. Therefore, your delta H will be equivalent to negative 2856 kilojoule. Right, but this is not the end, because in the question, you were asked to calculate the molar enthalpy. So the molar enthalpy means that you want it to be in 1 mole only. So, for example, here, you have 2 mole of ethane around here. So this much of ethane, you will produce this much of energy. So now you're going to calculate what is for 1 mole of ethane. Right, so from here we know that 2 mole of ethane will produce delta H is equivalent to negative 2856 kilojoule. Therefore, if you want to get 1 mole of CuH6, so your delta H will be negative 2856 kilojoule divided by 2. You should get the delta H is equivalent to negative 1428 kilojoule per mole. Right, so this is the final answer for the third question. Let's move on to question number 4. Approximate the change in internal energy resulting from the expansion of gas from 10 liter to 30 liter against an external pressure of 280 m and additionally having absorbed 100 joule of heat. Okay, so in this question, you were given the changes of the volume, which is the delta V, right? So you know that when you have delta V, so the formula that you can use is your W. W is equivalent to negative P delta V. So what is your P? So it states here against external pressure of 280 m. So your P is 280 m and your delta V is V2, which is 30 liter minus V1, which is 10 liter. So you will get 2 times 20. So it's equivalent to negative 40 ATM liter. Right. So now in the question, you were asked to calculate the internal energy. So basically, when we want to calculate internal energy, the unit should be in joule. So what you need to do is to convert this. So 1 liter ATM, so you need to convert into joule. 1 liter ATM is equivalent to 101.3 joule. So having to say that means that what we need to do is 40, you need to times 101.3, so you will get 4052 joule. And remember here we have negative, so we put on the negative over there. Right. Another thing is that in the question it states here that it absorbed 100 joule of heat. So your Q, since it is being absorbed, so it should be positive. It absorbs heat, right? So you want to calculate the internal energy, which is delta U. So delta U is equivalent to Q plus W. So given to you, the Q is 100 joule plus your W is negative 4052 joule. So you will get your delta U is equivalent to negative 3952 joule. So this is the final answer for the fourth question.
Question number 5. At 673 Kelvin, sulfuryl chloride gas dissociates to produce two gaseous products. When 1 mole of sulfuryl chloride dissociates, the equilibrium mixture was found to contain 0.75 mole of chlorine with a total pressure of 135 Pascal. Calculate the Kc for the reaction. Alright, so just like the previous question, the first step that we need to do is to write the balance equation. So we have the sulfuryl chloride, so SO2Cl2, it will dissociate into SO2 plus Cl2. So there's no need to further balance out the equation because everything is balanced already. Right, so from here what we can do is we need to write the ice diagram. So the ice diagram, so initially it gave you that when 1 mole of sulfuryl chloride dissociate, so at equilibrium it was found that 0.75 mole of chlorine is produced. So eventually what we are going to do is we write at first
it's just 1 mole and there will be no product being formed. So this one is minus X, positive X, and positive X. So here will be 1 minus X, X and X. It stays here that at equilibrium 0.75 mole of chlorine is being formed. So here we can say that your X is equivalent to 0.75. So we are going to write it again, 0.75. This one should be 0.75 as well. So 1 minus 0.75. Right. So in saying that, we will have the number of mole here will be 0.25 and the rest will be 0.75. Okay, so this is your ice diagram. So from this ice diagram, what we can know is what is the total number of mole. So we are going to use this value of the number of mole to find what is the total number of mole. Okay, now we are going to calculate what is the total number of mole. Total number of mole is equivalent to 0.25 plus 0.75 plus 0.75. Therefore, you will get the total number of mole is equivalent to 1.75 mole. Right. So, what else are given in the question is the total pressure. So, the total pressure is equivalent to 125 Pascal. But this one we need to convert into ATM. So we divide with 101,325. Therefore, you will get 0.0012 ATM. This is the total pressure. So you have the total number of mole and also the total pressure. So since we have these values, we need to calculate again what is the mole fraction as well as the partial pressure, because you are going to calculate first the Kp, then followed by the Kc. Alright, let's continue on. So we first want to calculate the mole fraction. So mole fraction, so for the first one is 0.25 divided by the total number of mole, so 1.75. So the rest are the same, 0.75 divided by 1.75 and 0.75 divided by 1.75. From here, you know that the mole fraction is equivalent to 0.1429 and 0.4286. So this one should be the same. Okay, so since you have calculated the mole fraction, what we can calculate now is the partial pressure. So the partial pressure is this value of mole fraction. You need to times the total pressure. So all of this number, we need to times 0.0012 ATM. Right. So then only you get the partial pressure for each component from the reaction. So after the calculation, you should get this value. The partial pressure for SO2Cl2 will be 1.7148 times 10 to the power of negative 4. And also for the SO2 and Cl2 is equivalent to 5.1432 times 10 to the power of negative 4. That is the partial pressure. So what we are going to do now is we are going to calculate what is the value of Kp by using these values. Right, so for the Kp is equivalent to whatever at the product. So partial pressure of SO2 times partial pressure of Cl2 divided by the partial pressure of SO2Cl2, right? So what you need to do is you just plug in the value here. So I'm just going to write 5.1432 times 10 to the power of negative 4, because this is the same value, so square, divided by 1.7148 times 10 to the power of negative 4. Therefore, your Kp should be equivalent to 1.5427 times 10 to the power of negative 3. Right, but if you look back at the question, you were asked to calculate what is the Kc, not the Kp. So we are just going to go through this again. So from this equation, what we can find that all of this is in gaseous form. So we know that your delta N is equivalent to whatever at the product minus whatever at the reactant. So we have 1 mole of chlorine and 1 mole of sulfur, SO2. So 1 plus 1 minus 1 mole of SO2Cl3. So just minus 1. So equivalent to 2 minus 1 is equivalent to 1. So that is your N. So moving on, you need to find your Kc. So the only formula that you can use to calculate your Kc is by using Kp is equivalent to Kc RT to the power of delta N. Right? So I'm just going to write here, all of these are in gaseous form. Alright, so from here we need to just plug in the value that we have calculated just now. So your Kp is equivalent to 1.5427 times 10 to the power of negative 3 is equivalent to your Kc, and then your R is 0.0821 and the unit will be liter atmosphere divided by mole Kelvin, and then your temperature will be 673 Kelvin. So this value you need to do to the power of 1. So in saying that, you can calculate your Kc is equivalent to 1.5427 times 10 to the power of negative 3 divided by, because you have to press your calculator for that, so you should get 55.2533. So you get your Kc is equivalent to 2.7921 times 10 to the power of negative 5. So this is the final answer for the 5th question. Right, so now we are at the final question for test 1. The value for Kc of a hypothetical reaction of 2A to produce B plus C is equivalent to 2 times 10 to the power of negative 3. The initial concentration of A, B, C are 3 times 10 to the power of negative 4 molar each. Briefly explain the direction in which reaction will proceed. Okay, in this question, it says here that the Kc is equivalent to 2 times 10 to the power of negative 3. But you were given the initial concentration of A, B, and C, which is 3 times 10 to the power of negative 4. So since you were given the initial concentration, what you can calculate is the Qc. So you were given the equation 2A will produce B plus C. So your Qc should be equivalent to, because you were given the concentration, so whatever in the product, concentration of B times concentration of C divided by whatever in the reactant, concentration of A, but because you have 2 here, so you need to do to the power of 2. Right, so given in the question also is the concentration itself. So 3 times 10 to the power of negative 4, because the concentration is the same, I'm just going to do square over that. So the bottom one will be the same as well. So you will get your QC is equivalent to 1. So your QC is equivalent to 1. Your KC is equivalent to 2 times 10 to the power of negative 3. Right? So in saying that, your QC is actually way bigger than your KC, because your KC here is negative 3. So your QC is 1. So 1 is bigger than whatever negative value, right? 0.00. So it means that when your QC is bigger than your KC, so the reaction shall move to the left until the equilibrium is reached. So it means that it will produce more reactant as compared to the product. So this is the final answer for your 6th question.
Alright, so this is the end of this week's video. I would like to thank all of you for watching this video from the beginning till the end. I hope this video will help you to understand how you should answer test 1 question. So I'll see you again next week. Take care and be good. Goodbye.